Okay, so this is Module 19, and we're going to introduce the concept of writing our own functions in this module. So we've certainly already written one function in each one of our programs that was called the main function. And initially we just described that as sort of a grouping of code. Now we'll start to write additional functions in our programs and call them. And certainly we've already seen how we call functions. We've called mathematical functions from the CMath library. We've used the random function. We've used several of the time functions. We've used several different functions in the previous modules. And now this is just adding on to our ability to write some C++ code. So this, I'd point out very specifically, functions can be a little bit of a tricky concept the first time you see them. I'd highly advise you to read the textbook 6.1 through 6.3 very carefully, actually even before going through these slides. This is a crucial concept. The rest of the semester will rely heavily on your ability to understand functions. And more importantly, as you continue on in computer science and you write larger programs, it's absolutely impossible to continue to be successful without really understanding and mastering the concept of creating functions. So it's a very crucial topic. We'll cover it in a couple of different modules. So first off, let's just kind of motivate the problem a little bit. If we were going to, let's say I was going to ask you to write a program that computes the sum of all integers between 1 through 10, for instance. And without actually even writing the code, we could think about this as an accumulation problem, right? So we could, so if we're talking about numbers 1 through 10, right? So the sum, really we would probably just do something like int sum equals 0. That would be our accumulator. We'd write a for loop, maybe started at 1, I less than or equal to 10, I plus plus, and each time around the loop we do sum plus equals I. All right, that's our standard accumulation for loop. We could do it with a while loop. We could do it with really any construct. So now let's assume that we were going to do this instead from 1 through 10. We wanted to do it the sum between 20 and 37, sort of a random picking of numbers. Well, if we wanted to do that, it would really be pretty much the same problem, right? It would just we would go and we'd start our loop at a different value. Right? So we wouldn't start it at 1, we'd start it at 20. We wouldn't end it at 10, we'd end it at 37. Right? And this for loop would go ahead and generate 20 plus 21 plus 22 and all the way out to 37 and give us the sum. If we tried to do this with 35 and 49, probably get the pattern here. We would just be changing our parameters. So we would do 35 through 49, and again we do 35. That for loop would just do 35 plus 36 plus 37 all the way equal to the sum. So one of the things that we see here is that almost all of this code, with the exception of these parameters, is the same. It's exactly the same bit of code. And if we were to write a program to do all three, we certainly would have a lot of duplication. And we've talked a lot when we dealt with conditional execution about how we hate duplication. We don't want to duplicate any of our code to the best of our ability. And so functions really just are born out of this desire to not repeat the same code or virtually the same code each time we want to do something. So if we switch back to the slides, to kind of drive this point home, I've got the full code written for all three. We can see the comparison very easily. We've got the first sum through 1 through 10. We've got the sum through 20 to 37 and 35 through 49. And we can really clearly highlight what's changed. Right? So the purpose of a function is to be able to write the code that's sort of grayed out right now with placeholders, what are going to be called parameters that can be configured when we call them. Right? So when we call this eventually what will be a function, we're going to pass in as parameters 1 and 10, or 35 and 49, or 20 and 37, and we can reuse the same exact code to produce the answer, or to produce that printout in this case. So the function is best thought of as a reusable group of code, a reusable sequence of statements that would be beneficial to call several times with different parameters. Functions can not only accept parameters, but they can return results. And we'll see versions of functions that don't accept parameters, that don't return results. We have some options available to us. We've certainly already used some functions like this. For instance, the random function does not have a parameter being passed into it. Parameters aren't required, but often are very, very useful. We've already seen how we call functions with parameters. So the power function, for instance, has some code in it, some reusable code that calculates the power of 2 to the 8th, but would also calculate the power of 3 to the 16th if we pass that in. We know that the power function returns a value. It will return, in this case, 256 and place it into x. So we know how to use functions. We sort of understand, hopefully, what they're all about. We're using this stuff. Now we need to learn the syntax for actually defining these new functions. So I've gone ahead and I've written a function. It doesn't print out. It actually instead just returns the sum. But this is a function that would compute the sum between x and y, inclusive. It's doing exactly the same thing that we've done in the past. So if you look at this code very closely, we've got a local variable being declared, and it looks like I lost a semicolon here for some reason. Let me add those. The rules of C++ is the same within functions. I'm creating a variable within this function, and remember our scoping rules. Just like if this was an if statement or a while loop or anything else, this S variable is only visible between these braces. Now the difference between this declaration right now is that this is not going to be inside main. This is going to be outside main. Functions are not defined within other functions. So that's different than learning about while loops and if statements and switches, which are all sort of assumed to be inside of main. So we create a variable in a function. We go through in a for loop and we compute the sum, and notice that those x and y variables now are playing the role that we saw over here. Right? So they're being plugged in the exact same spot. We're using placeholders called x and y. Now those placeholders are important what we name them. Those are declared as parameters. So if we think about what main looked like, we had int main and we had an open and close parentheses and then braces. For sum, it's an int sum with the parameters within these parentheses. Main did not typically accept any parameters. The return type is signifying what kind of data this function will end up returning. Main actually can return 0, right? And we can call return 0 to stop main. That's why main had int ahead of its name. We can return other integers obviously as well, but typically we just do return 0 for main. So we go through the for loop, we compute the sum, and now we return the sum back. Okay. So this side just kind of summarizes this. Now functions have names, and don't know what happened when I was writing these slides. Let me just fill in what I had before. Let me add those semicolons as well. Functions have names and they follow the exact same rules as variables. So if you remember variables, their names had to start with an alphabetical value, an alphabetical character, or an underscore. And then after the first character, it could be numbers. So we can have a function called f1 or something like that. We can't have spaces in function names, and we can't have special symbols like dollar signs and pound signs and that kind of stuff. The XY parameters, really you can think of them up here. They look a lot like function variable declarations without a semicolon, of course. And in fact, they very much are separate variables that are being created and are actually tied to this function. But they're special in that they're going to be initialized with whatever the user or the user of your function, which is probably you, uses when calling the function itself. We have local variables, and then we return the value. So the caller in this case, when I say the caller of a function, when we were writing our programs to use a CMath library, when we were writing programs to use the random function, we were the caller of those functions. We didn't actually create those functions. We didn't implement them. We called those functions. Those functions return something to us. Now we're sort of looking at it from the other perspective, and we're going to write some functions that will return back to the parts of our programs that call those functions. So now we see, now I'm showing you the whole thing sort of starting to be put together. And again, I copied and pasted quite a bit, so I'm going to add those semicolons. Now we've got our function, and this is the context that this function will be defined in. Notice that it's completely outside of main, and for now, for the time being, we're going to keep all of our function declarations above main, and we'll talk about how to fix that later on. So we've got sum, and we've got main down here, and notice that main is calling sum, just like we would call the power function, just like we would call the square root function. It's calling sum with parameters. Right, so 1 and 10, 20 and 37, 35 and 49, and it could call it with anything it wanted. Right, so my main function is essentially the caller of sum. Notice that main does not have any variables called x, y. It could. If it did, that really wouldn't make a difference. Variables called x, variable called y in main has no effect on the variables that are attached to sum. Remember our scoping rules. If we declare variables of the same name in different parts of an if or an else, they're not the same variables. The same thing goes with functions. The variable a, b, and c is not available within sum, unless, and we could create local variables called a, b, and c, and it still wouldn't mean that they're the same thing. They're separate and distinct variables. So I call sum, I pass 1 and 10 in. Now, when I do that, and let's think about what will happen in memory. And I just copied over this code so we can look at this. Let's imagine that we are sort of entering into main. We want to start to think about how these variables act in memory. So we start out by creating a variable a in main. We're going to have declarations for b and c as well, so might as well just draw them. And when we call on the first line, we're going to call sum, and we're going to call it with 1 and 10. When control shifts, and what we're really doing is that the next line of code will not be the very next line of code. The next line of code called will be up at this sum. When we call sum, we're going to enter into that function a variable called x, and a variable called y, and a variable called s is going to be created. They're distinct. 1 is going to be copied into x. 10 is going to be copied into y. Sum starts out at 0. We're going to go through, we're going to walk through, and I guess the summation of, I don't know what the summation through 1 to 10 is. I'm not going to worry too much about that, whatever that might be. That's going to be computed. And then that number, when we return it, it will go right into this a variable. And so doing that offline a little bit, that's going to be 55. The summation of 1 through 10 is going to end up being 55. So once we return out of this function, however, the other thing that we need to be aware of is that the variables that were created alongside of sum get wiped out. They are going to go away as soon as I make that return. And that's important, because the next time that we go ahead and call sum, so let's skip back here. The next time we return back, and now a is 55, and we call sum again, we're going to create brand new variables called x, called y, called s. S is going to start at 0. X is going to have 20 now. 37 is going to be copied into y. And we're going to compute the summation between 20 and 37. And this I'll put as summation number 2. And we can calculate what that is offline. The next time once sum gets returned, these variables go away. We're going to call sum again. 35 is going to be copied into x. 49 is going to be copied into y, and away we go. All right, we're going to return that new variable, and we're going to store that in C, and we'll call that sum number 3. And then at this point, my cout statement will print out all 3 variables. So each time we call that sum function, brand new variables, some of them will be parameters that will be initialized. But notice that I didn't draw them any differently because they're fundamentally the same thing. They're not anything really different. And then I also have my s variable recreated every single time as well. Local variables within functions are created and destroyed as we enter and exit functions. In main, we never really worry about that because when we exit a function, of course, our program's done, so we don't really have any use for those variables. So when we call a function, we've already sort of talked about this to some extent. Parameters can be any expression that yield the right data type. So we've seen plenty of examples with integers being passed into sum. Of course, if I had a variable called w and z, I could pass those in as well. That's no problem. And the value of w would be copied into the value of the first parameter, x, in sum. Sum called with an expression with w plus 1, with z plus w. Again, the same thing would happen. This would be evaluated, whatever that variable and that, the mathematical expression evaluated to, that number would get copied in. And copy is a really important word that I'm saying in here. It gets copied into those parameters. When I pass w in, it's not sort of making changes to w, it's not affecting w, it's copying w into the first parameter, it's copying z into the second parameter, it's making a copy of this answer into the second parameter. And in fact, I can call sum of 5 to 10, and that will execute. That function call, sum, will actually enter into sum with 5 and 10 as x and y, as those first 2 parameters. We'll evaluate it, pass the result back. We'll then evaluate this, the 30 through 100. We'll pass the result back. Then once we have both of our values, we'll actually go ahead and call sum a next time and calculate the summation between those 2 numbers. So even though this looks pretty complex, and I don't know why we would really calculate this, there's nothing special about any of these different ways we're calling functions. From the perspective of sum, go back to the declaration, from the perspective of sum, it's going to have a value of x and y when it gets called. It doesn't matter how complex the process was to figure out what x and y was. So if we go back here, it doesn't matter whether x and y came from the return result of a function, from the return result of some other function. We could call this with sum random. It doesn't make any difference. When we call sum with 5 and 10, 5 and 10 are going to be copied in here. When we call sum with 30 and 100, 30 and 100 get copied in. When those return results come back to us, whatever that value was, get passed into x and y for this function call. Now, the order of declaration, I mentioned that we'll declare our functions above main. The order of declaration actually makes a difference in this case because the compiler, the C++ compiler goes top down. And it does sort of it's a 2-pass compiler, but from our perspective right now in terms of the code, it's a single pass through the entire source code. So the compiler would start at line 0 and it would start compiling. So if I wrote this program like this, When the compiler started to see int main and it saw that we called compute sum, it would throw an error because it's never seen compute sum before. It doesn't know what that is. It doesn't know whether you're using it right. It doesn't have enough smarts built into it to go through and actually look at that compute sum function call or the sum function call. So even though you have the function declared, the compiler walks down line by line, and if you use a function before you define it, it's going to end up in a compiler error. So in this case, in this compute sum, and I named it sum on the previous slide, this compute sum function is fine, right? It'll see the declaration. Notice it won't execute it, right? Your functions always, your program always starts in main. But the compiler sees compute sum first. It learns how it's supposed to be used. It's supposed to be used with 2 parameters. It's supposed to return an int. And now it can see that you're using it correctly. When you use compute sum later on in your program, it can verify that you're using the right syntax. So we've seen a lot of terms here introduced with functions, and they are very important that we have a clear understanding of what they mean. Each function can have its own set of local variables. That variable is associated only with that function call. Or with that specific function. So all of the variables up till this module that we've created were in fact local variables for main. Now we're going to create possibly local variables in some of our functions, and we do so for all the same reasons. What's important to remember is that local variables are only available, they're only visible within that function. Local variables in function 1 called x is not the same as a local variable declared in main called x. The name does not really matter in terms of local variables when we're spanning across functions. They are always independent of each other. Parameter variables within a function are a little bit different because although they only exist within that function, they're only available within that function, they also represent a way of communicating from a calling code, calling function main, to the function. Because parameter variables are initialized automatically with what values the user called them with. And the user, again, I'm substituting user and caller sort of interchangeably. So parameter variables, their names don't necessarily have to line up with anything inside main, inside the calling function, but those values are going to be initialized with what you call them with. Return values are not really variables within the function, but they are data that gets passed back to the caller, back to main, back to the user of your function. The caller has the responsibility to place that data into a variable if they're going to use it. So if we look back over here, main saved the return result. So the return result, you can think of it as the result of this expression. It assigns it into S. If it did not, if instead it just sort of just called this, right? Well, compute sum wouldn't change. Compute sum wouldn't care. The code would be perfectly fine. It would still work. It would still return sum, but I'd never be able to access that value. It's key that the caller actually does capture the value and store it in a variable or perhaps just print it out. But that's not the function's responsibility. The function's responsibility is just to return the data. So as a first example with this, programming example 23 is looking at sort of writing our own version of one of the CMath library functions. So we've used the power function several times in our programs, and the power function accepts 2 parameters, a base and an exponent, and it will return back to us the result. So what we're going to do here is we're just going to write our own power function. Rather than including CMath, we're going to do it ourselves. We'll do it in a little bit more restricted form. We're going to only deal with integers. The power function in the CMath library is a lot more complex because it deals with doubles, in particular doubles as the exponent. We're not going to deal with that right now. So I'm just going to design some code that does the power function for integers. Before I do this, just word of caution: you never want to actually, in the real world when you're actually programming and getting paid to write code, you certainly don't want to re-implement functions that are available to you in a library. You want to use those unless there's some reason to believe that they're not appropriate, which is fairly rare. Certainly the things in CMath have been very well tested and are very optimized. You wouldn't want to write your own power function for any other reason other than to learn. And so just that's my little disclaimer before we actually go and re-implement the power function here. So let's just think about how we would go about doing this power function. Let's take an example, 2 raised to the 3rd power. We know it's equal to 8, but how do we write some code? Forget about writing a function necessarily right now. What this really evaluates to is 2 times 2 times 2. So the base, or the exponent, I'm sorry, is telling you how many times to multiply these values by, right? The base. If it was 3 to the 4th power, we know it would just be 3 times 3 times 3 times 3. So this is kind of an accumulation problem. But the accumulation is not the result of a plus, it's the result of a multiplication. So what we probably want to do is start with maybe product. We don't want to start this with 0, right? Because if we start it with 0, it's going to cause problems for us when we actually start our first trip around a loop. I probably would want a for loop int I equals 0, I less than, and let's call this e, and let's call this b. So really our function is going to be b to the e, right? Less than b, I plus plus. I'm writing a for loop that simply goes around, less than e. It simply goes around e times, 3 times, 4 times. And each time around that loop, I'm going to say product times equal the base. So if the loop goes around 4 times and the base is 3, 3 times 3 times 3 times 3. Really, the first time around the loop, it's product equals 1 times 3. And then the next time around the loop, it's product equals 3 times 3, because product is now, of course, 3. And now this is 9, and we do the same thing, equals 9 times 3, and then 27 times 3. So the product of 1 is important. If we initialize this at 0, well, then this would have been 0 times 3, which would give us 0, and then this would be 0, and on and on. So whenever we're doing an accumulation type problem, normally if we're just doing sum or adding, we would start the accumulator, whether we call it sum or not, at 0. For multiplication, we want to start it at 1. We want to start it at whatever the identity is for the particular operation that we're accumulating on. So we've got sort of a general outline of how we would do this, right? We've got a product started at 1. We've got a for loop that goes around e number of times and multiplies by the base each time. Now the question is, how do we put that into a function? And that's better just done in the regular code. So I'm going to start by writing, and notice I'm not including CMath. I'm going to start by writing my power function. Actually, Visual Studio includes the power function automatically, it includes CMath automatically, so I'm going to call this my power instead, so I don't get any conflicts. I've got base int exponent. So those are my 2 parameters. When I call this, so let's actually, just so we can get this to compile, I'll say return 0. When I call it, I'm going to say, and let's ask the user for some numbers. Enter base and exponent. And we need some values. Base exponent. Right, so I'll read in those 2 values from the user. And now I'm going to actually call it, maybe say result equals my power base exponent, and I'll see out the result. Okay, so that's how I'm going to use my power function, but I'm more concerned about how I'm actually going to write this code. And it really comes right from our notes, right? So it's basically the same thing. I called it base and exponent, or exp, instead of b and e, but otherwise it's exactly the same. So I'm going to have a local variable product, starts at 1, for int I equals 0, I less than exponent, just go around exponent times. And we're going to multiply product times equals the base, and we'll return back product. Okay. So let's go ahead and build it. And we'll enter in 2 and 3, and we get back 8. If we enter in 5 and 2, we get back 25. If we enter in 9 and 5, we get over 59,000. Right? And so those numbers are looking pretty well. Now, I purposely called the local variables in main base and exponent, and the parameter names base and exponent. But I did that not because it's required, but to prove a point. I can call these numbers anything I want. And the result is exactly the same. There's no difference whatsoever about those two variants. There's no requirement to name the variables that you're passing into this function the same as what this function expects it. This function is not saying you have to give me variables called base and exponent. This function is telling you that you have to pass integers. Within the context of this function, it's going to call the first integer base, and it's going to call the first integer exponent, but it doesn't care whatsoever what you call those first values here. And to drive that home, we know that we can also call my power with 4 and 4, or 4 and 3, and it works just the same. There's no difference, and there's no way my power inside your code doesn't care whether this first variable is coming from x and y, or this first and second variable is coming from literal values. It doesn't make any difference. So don't feel that you need to name these variables the same, and don't feel that that's going to do anything for you, naming those variables the same. Sort of by definition, when you write a function, it's reusable, and it's going to be used with all sorts of different parameters with all sorts of different names. The parameter name that you declare up in this function is only relevant for within this function.